So this is the clip everybody has been waiting for. I know it, there's no other way, because this is a Tesla coil. I did not build it by myself. This was from a eBay seller, a German one. He sells this Tesla coil in combination with the driver for around 250 euro. So not that cheap, but I hope it will work fine. I actually just tried it and yes, it does. So here we got the Tesla coil, then the driver. The low voltage side is already powered through my lamp bench power supply right here with 12 volts, draws 120 milliamps. And the high voltage side is connected to mains wiring, as you can see, but not directly to the outlet or sockets. It is connected in between with a variable transformer so that I can control the voltage, because as you will see in a second, even with 25 volts AC, there are sparks, so I can only imagine what 230 volts will be like. So not very safe for me to use in my small lab here. I don't want to kill any components, any equipment, so I'm just playing it safe here with 25 volts, because the video itself will not be primarily about the Tesla coil, but instead about how to drive these two, I think those are MOSFETs or IGBTs, not sure. And as you can see here, this circuit uses a gate drive transformer, and that will basically be the subject, how to drive MOSFETs or IGBTs with gate drive transformers. We will look at different waveforms, maybe build our own, look at commercial solutions, what to look out for. And that is why this is only a practical example. And I should not talk anymore, it's getting boring. Here we also got an energy meter to see how much power we draw from the input, because this transformer can only handle 500 watts. But nevertheless, this is just my small test setup. So let's just crank it up to 25 volts. And as you can hear, there is a familiar sound. I hope you can see that. Let's try to change this a bit. And right now my touchscreen is still working, which I'm thankful for. I tried this clip before and I used this screwdriver here to touch the discharge, the arcs. But if I do that and have my smartphone in my hand, it completely freaks out. So I will not do that again. You can see it here. We got the discharge. We can control it with the transformer. We can go all the way off and then back to 25 volts or a bit higher, you know. Yeah, it is. I'm very happy with this kit. Looks very awesome. And yeah, that it works, which is great news. And I will see how well we'll continue with the video. This was just the first basic test for it all. And I hope it will be very interesting. I think so. And I think now I will start winding my own gate drive transformers and then see how they perform, what you have to look out for, and then create a script. So it will take some time, but we will get there, I promise. So I'm still working with the Tesla coil driver circuits for the Tesla coil, obviously. And what I'm currently probing here is basically the output of the self-made gate drive transformer. So here we got the input. It is connected to two MOSFET drivers, which basically create a square wave with the frequency. I think right now it is around 184 kilohertz. It is not tuned. The Tesla coil is not on. There's the base frequency, and what it basically does, the drivers, is connecting the primary side of the transformer to the supply voltage and then to a negative. So we got a square wave, which basically will be created on the two secondary sides, because there are two of them. And I'm probing them right now. And here they are, as you can see. Look pretty decent. As you can see, we got a green one and a yellow one. Of course, they're out of sync. So one MOSFET is on, then the other is on, and then the other way around. And they look perfectly fine. Of course, they have a small overshoot, if you can see that at the start there. So you can easily solve that, I think, just by adding a damping resistor, adding a bit more damping to get rid of the overshoot at the beginning. But other than that, very nice waveform. They are pretty much flat when they reach the amplitude then. And there's no big ringing, I would say. No, not really. Just a bit of an overshoot, but really good waveform. So that works perfectly fine. And now I will try to make my own and then show the difficulties, what goes into that, and do a couple of tests. And I hope I will get the script done pretty soon. So a new video is almost done. This time, this is the reason for the video, why it started. This is actually not just the PCB, it actually comes in such a casing here. Not sure if you can see it. It is the OT Arc, which is actually a power measurement tool. So you can basically hook up any kind of device there and then measure the current and voltage it's consuming. And this device then can spit out the power consumption. Such a device I already built it in a previous video, which was a power measuring tool, which could also calculate the energy. But this one is special because it can measure very low currents. So something in the microamp range and the nanoamp range, this thing can measure it. And that's what I try to do with my not sure if you can remember this. This is my old TV remote, not TV, just an infrared remote that I built for a speaker system. And when it is currently in sleep mode, if I push here, it wakes up. And with those buttons, it sends out the infrared signal. And in sleep mode, it actually consumes very low currents, like sometimes even as low as 100 nanoamps. And up to 1 microamp, so very low current levels. And in the video I basically try out the product. Spoiler warning, it works very well. I'm very pleased, and if you can see on the PCB, they put a lot of effort into getting rid of noise. You can see here in the middle there's the amplification area, and yeah, there are lots of countermeasures against noise, so it works really good. And then we got my DIY attempt, because this is a DIY or buy episode. So here we got an op amp, the OP177. I think you cannot see that completely, but it is an ultra precision op amp. And with that, I just wanted to try out a couple of things, see if I can actually go that low, to measure that low of current. I don't want to spoil too much here, you will see it in the video. I got some results, mixed results I would say. All in all, DIY does work to some extent, but if you go into microamps and nanoamps, a DIY design will mostly not cut it. But I still played around a bit with the Teensy here. I did the measurements with the Teensy. It has a 16-bit ADC, and this then sends the data over to the computer, who processes that through processing, and spits out a nice graph, which looks something like what the OT would spit out. So interesting episode, I think it will be. Currently finishing up the filming, and then the video should be done soon, and I hope it will be interesting. So here is a new video I'm working on. This is a PCB, but it's not your usual kind, as you can see. This is designed from the Volterra Punk console. So here are the components for that. So you got a buzzer, here is a 556 timer, I think. It was just supposed to create some square waves which you can adjust, and then create some funky tones with all of those components. But as you can see, there's a problem with this PCB. First off, the way I got this PCB was actually like this. So it is just a blank PCB board. So this is actually completely made at home. This is printed onto the PCB. So I'm currently testing a machine which is right by my side. I don't want to spoil too much for now, but this machine can basically lay down those lines here. That's conductive ink, they call it like that. And it lays it down, it then bakes it, increases the temperature so that it becomes dry, and then you can solder components to it. And this is actually a double-sided design. It took me quite a while just to get used to the machine and trying out a couple of things and doing all of that. So precision-wise, it's awesome. It worked so well, no problems at all. But I made one mistake, and that is while baking. There is actually there is a, I don't know how to say it in English. There is a layer between the heated bed and this thing, the PCB, which is for sacrificing when you have the drill and goes through. So it does not directly drill into the heated bed. And I actually forgot removing that. So while this side was baking, I realized that, but at that point it was too late. And then I did this with the other side, the baking, but then I removed the board, the extra board. And as you can see here, don't do that like I did it, because now I was trying to solder, and as you can see, the ink does not stick to the board on the front side where I did it wrong. But then again, I tried that on the back side, and here you can see how good the ink holds up. So it can really take solder, but if you don't bake it correctly, then it doesn't. So, but that's not a problem. This was just the test example the machine comes with. I will now try to bring my own PCB design into this software and try to create basically a PCB at home without having to order it from a factory. So I think really awesome subject. I'm glad I can test out this machine, and you will see about this in the future. So we are back at printing PCBs. This is the one I talked about earlier in a previous clip. It printed perfectly fine. At the back you can see it soldered well, but the front I made a mistake, so I cannot test this electrically. But then I wanted to continue with a practical example, and this is a dimmer I made in, I think, a video 2 years ago, which was about dimming, the problems of dimming, and this was based around an FL5105, I think I see. I removed it here because I actually only had this one, not sure where the rest is. That's the problem with my organization sometimes. You don't find stuff. So I basically redesigned this circuit a bit so that it doesn't have a copper layer here, because of course with such a big layer of conductive material, that's hard to print for such a printer where the ink is quite expensive. So I redesigned that, did a couple of things, and it turned into that. So this is basically the finished circuit. Everything soldered is onto it. There are vias which go from the top to the bottom. It is double-sided. It looks a bit wanky at the potentiometers and the switch, but other than that, I tested everything, and as you can see, it works. Like, it's powered with AC voltage, as you can see here, and it really does work. Now, of course, me filming and trying to adjust something here to prove that to you will be... Oh my god, it will be impossible. Nope, you have to trust me. You will see it in the video. So this thing works perfectly fine as a circuit. It works with AC voltage, as you can see, 230 volts. No problem whatsoever. So this is a very interesting technique for prototyping, I think. Just if you have, for example, such an IC, an SMD IC, maybe with more pins, and you don't want to order a PCB to just connect it with a couple of components and test things, I think the printer is actually really useful in such a case. Because it's quick, you can do it in-house. And there are other advantages I will talk about in the video. Of course, there are disadvantages to such a technique, but overall, very interesting stuff. I really liked trying it out. And yeah, you will see it when the video is done. So, what are we looking at here? This is a breakout board for USB Type-C. I got one right here because currently I'm working on a small project where I want to use the power of my phone, which is currently recording this small clip. So I have a USB Type-C port at the bottom, and you can basically plug this in, and you got a couple of breakout pins, not all of them, but for me it was important to have the supply voltage and ground. And what I thought initially, if you plug it in, you get 5 volts, but you actually don't. So this is the original version of the circuit. So this is just a small quick tip. And here you can see they used a 56 kilo ohm resistor to pull something up. You can see it here. Here's the connection. It goes to both pads here, and then it goes to the supply voltage, pull it up. And what I read online was that this is used in some kind of configuration, and that is usually used with the CC pins, so the configuration channel pins. So I started to think, okay, if those are the configuration pins and this is pulled up, then I Googled and I found out that you actually need a 5.6 kilo ohm resistor soldered between the CC pins and ground, so that the phone or whatever USB Type-C device outputs 5 volts. And I think you can even draw up to 3 amps with that. So this is basically, you can see it here, horrible soldering, like always. No, I solder decently, but this was not the case of a good solder connection, but it worked, as you can see. Here we got the connection to the CC pins, this time pulled to ground, and this is a 5.1 kilo ohm resistor. And as soon as I plugged that into the phone, it activated. You got 5 volts on the output, on the ground pin and the supply voltage pin, and yeah, you can use it. So yeah, small quick tip if you ever want to get 5 volts from a USB Type-C device. So as you can see, I built something new. This time a more basic project video, I think. I wanted to build something like this for quite a while, a couple of years. I had this idea, and the idea actually started with my smartphone, which I'm filming this with right now. It was about hearing audiobooks with my smartphone, and I realized that sometimes the audiobook volume is really there are only exceptions when this happens, is quite low. And that's when I thought about, hey, why not create a small amp that you can plug right into your smartphone. Like you can see it here, you got your audio inputs, then here is a USB Type-C port. If you saw the last clip, this is how I get power. And then basically here we got the little amplifier circuit, and down here an output jack for headphones. And yeah, this is basically the project. In the video I will describe, this is actually a Class A amp, a stereo Class A amp. I will basically describe how a Class A amp works. It is very simple, but the quality is quite awesome. Actually, the efficiency is not great, but since we're using headphones, which is a small load, it will be just fine. The current for this is like 40 to 50 milliamps, the quiescent current, also the max current pretty much. So you can power this with your smartphone for quite a while, but yeah, then again, the efficiency is terrible, but you will see that in the video. And I'm really happy with the outcome. So it's not hard to calculate, not that hard. The parts are pretty basic, so this is a project you can definitely try at home if you want to tinker a bit with electronics. And as a bonus, I also designed a small enclosure here, so that will fit in here very snugly. Yeah, I'm not pushing it down right now, but then I also got a small lid here that plugs on there, and then yeah, you got your really basic stuff, but it came out very nicely, I would say. And yeah, you will see that in the video. The video should be done soon. Those will be the last recordings. I just added a bit of hot glue for the USB Type-C port for stability. But other than that, I hope you will enjoy this small project. Something very basic, but I want to do that for a while, and I feel like viewers also enjoy such basic topics because it's still very interesting, and you will see it in the video. Okay, that's enough for now.